Hello and welcome to video lecture number 10, which covers section 1.6, a library of parent functions. As always, take a moment to read today's objectives. A large majority of the functions we deal with in this course and in all of mathematics stem from one of these 8 parent functions. Therefore, it's very important for you to study and understand the general trends and shapes of these graphs. Example 1 asks us to perform a mini-analysis of each and every one of the 8 parent functions. The first graph we will take a look at is the identity function, and this is the basic linear parent, or y equals x. So take a moment to sketch the graph as you see here. Notice it does pass through 0, 0, and the slope of this line is 1. First of all, with letter A, this is an odd function because it does display origin symmetry. The domain and range are both negative infinity to infinity. There are no restrictions whatsoever for x or y. There is no change in direction. This graph is increasing the entire way, so there are no relative minimum or relative maximum values. Since it's increasing the entire way, we will say the interval of x's is negative infinity to infinity. And finally, it does cross the origin, therefore the x and the y-intercept is located at 0, 0. Now we will take a look at the constant function, and the constant function appears as a straight horizontal line that intersects the y-axis in one spot. Wherever it intersects, we will call that the value of c. Going through part A, this is definitely an even function because it displays y-axis symmetry. If you fold down the y-axis, this graph will match up perfectly. Its domain is negative infinity to infinity, and its range is only one value. There's only one value of y that this graph uses, and it will be whatever that value of c is, or its y-intercept. This graph is constant. It does not change direction from increasing to decreasing, so there are no extrema. It is a constant function, as the name suggests, so it will be constant the entire domain, negative infinity to infinity, and it does not have an x-intercept unless, of course, it ends up being a line on the x-axis. But in any other scenario, the y-intercept will be wherever it crosses that y-axis. The next parent function you are very familiar with is known as the squaring function, aka the quadratic parent. This is definitely an even graph. It has y-axis symmetry. You can fold along the y and the graph will match up. Its domain is negative infinity to infinity. However, the range is not. Notice this graph doesn't use any negative y values. The range begins at 0 and uses any values that are greater than 0. So 0 to infinity is our range. There is a change in direction, so there is a local minimum value at 0, 0. This graph is decreasing from negative infinity to 0, and it is increasing from 0 to positive infinity on the x. And last but not least, that local minimum also serves as the x and y-intercept. Our fourth function we will look at is the cubic parent function, and it is given by the equation f of x equals x cubed. So I went ahead and labeled some of these points in case you were wondering what they were. We start with it being an odd function. It does display origin symmetry, and that is demonstrated. If you take a look at the point 2, 8, notice its opposite, negative 2, negative 8, is also on the graph. So when you look at any given point on this function's graph, the opposite point, meaning opposite signs, has to also be there, and that definitely holds true. The domain and range of this function are negative infinity to infinity. There is no change in direction. This graph is increasing forever, so it increases from negative infinity to infinity, and once again, we have an x and a y-intercept located at 0, 0. Our fifth parent function is the square root function, and I've shown the graph and labeled some of the key points. This doesn't display any symmetry at all because notice it doesn't span more than one quadrant. It stops at 0, 0, or starts there, and has only points in quadrant 1. Therefore, the domain and range are from 0 to infinity, including no negative values. It does not change direction. It is increasing the entire way, so there is no local max or local min. A lot of people will point this out that 0, 0 must be a minimum. Well, it's an overall minimum of the graph. However, this point is not a local min, because local min or local max points only occur when there is a change in direction of the graph, and there is no change in direction. The sixth function is known as the reciprocal function, or the rational parent, and please observe the equation. Notice there is an x in the denominator, and recall we cannot have 0 in the denominator. So that is why the graph will not touch the y-axis, nor will it touch the x-axis. So I want to point out specifically part D. Notice this graph does not change direction. Since it is in multiple parts, it may appear that way, but if you read from left to right, the segment in quadrant 3 is decreasing the entire time, and the segment in quadrant 1 is also decreasing the entire time. Since it does not touch the x nor the y-axis, it doesn't have any intercepts as well. The seventh function is the absolute value function, and if you remember what absolute value does is it takes negative values and turns them positive, and takes positives and turns them positive. So that's why none of this graph you will see in quadrants 3 or 4 in the negative y values. Notice everything appears in quadrants 1 and 2, or the positive y quadrants. So take a look at the A through E, and I'd like you to write those down as well. By now you're probably starting to get the hang of some of this analysis portion. So I'll focus again on D, the decreasing, increasing. Notice it's decreasing from negative infinity all the way until we get to 0 on the x, and then once again it starts increasing from 0 to infinity on the x, and therefore because it does change directions, there is a local minimum value at 0, 0, and that does serve as both the x and the y intercepts. The eighth and final function is known as the greatest integer function, also known as the step function, because as you can see, it looks like a series of steps. It is denoted with a double bracket on either side of x, and to produce the graph, it's also called the greatest integer less than or equal to x. Now, to me, I think it would be easier just to remind ourselves that we will round down every single time. So let me explain a little bit further. If you take a look at the x value of, say, 2.8, when I look up, I touch the graph at y equals 2. So what that means is that f of 2.8, when x is 2.8, we get a y value of 2. So notice what we've done. We've taken the x value, 2.8. Even though that's closer to 3, we round down to get its y value of 2, and that will happen for each and every case. Looking at some of the analysis pieces, A through E, you may notice that, oh yeah, it increases because as you read left to right, the steps are going up. However, what we do is we think of this as a series of constant pieces. See, these pieces are not connected, they're disconnected. So each piece itself is flat. Therefore, this graph technically has no increase nor decrease. Another point I will make is the x-intercepts. If you take a look at this segment specifically from 0 to 1, notice it crosses the x-axis in many, many, many places. So there are infinitely many x-intercepts. However, there is only one y-intercept at 0, 0. Example 2 asks us to take a closer look at the greatest integer function by evaluating it at certain specified x values. So I'm going to try example 2b with you, and I ask that you try example 2a on your own. So it asks us to plug in the value -5/2 for x. Well, that simplifies to -2.5, and that may be easier for us to use here, so I went ahead and used the decimal instead of the fraction. So just like any function you're asked to evaluate, you plug in the -2.5 or whatever x value into the function for x. Once I do that, I get this statement that reads -2.5 plus 2. Simplifying that, we end up with -0.5. However, we are not finished because notice there are still double brackets around this answer. So the greatest integer function, if you recall, asks us to round the value down to the nearest integer. So rounding down with negatives can often be a difficult thing to do. So I went ahead and showed you on a number line down below. If I have -0.5, the two integers it is between are 0 and -1. Rounding down means go to the smaller of the two integers, and -1 would be that value. The tendency here is to round that down to 0. However, that is not the next smallest integer next to -0.5. So our final answer will be f of -2.5 equals -1, because again, this function requires that you round y values down to the smallest nearest integer. So please try example 2a on your own and have it ready to check for tomorrow. The third and final example asks us to graph various piecewise functions, and recall that piecewise functions are formed from different equations put together. So in example 3b, you see a function that consists of 3 equations, and I've color-coded them with red, blue, and green. I'm going to start with the first one, 4 minus x squared. What I've done is I've entered it into a calculator, I've looked at the table, and I've plotted the entire graph that I can fit. I've done that in red. However, now you have to take a step back and look at the domain. The domain of this particular function says we can only graph this equation when the x values are less than -2. So what that means is everything I'm shading in black, we need to remove from this function. So I'm going to erase it now. So once we remove the portion of the graph that is greater than -2 on the x, we are left with the segment you see in red. Notice there's an open circle on x equals -2 because the domain says we cannot equal -2 with this particular equation. Now we will graph the second equation, 3 plus x. Once I graph the entire equation 3 plus x, I then have to look back at the domain and notice that it's telling me we can only graph this equation from -2 to 0. Therefore, I must get rid of everything I'm shading in black because these portions of this graph lie outside of the specified domain. After we remove the portions of the graph that are outside the domain, we are left with only the small diagonal segment in blue that you see for the equation 3 plus x. Now we will graph the third portion of the piecewise function. I've now graphed x squared plus 1, and notice again the domain. I'll take a look at the domain, and it says x can only be greater than or equal to 0. Therefore, I must remove any portion of the graph that is less than 0. I will do that now, and we will complete the piecewise function graph. So I've noticed a typo on my problem, and the domain originally for this last function in green was x greater than or equal to 0. Please change that to x is greater than 0. And what that means is we'll have now an open circle there because now look at the graph as a whole. You might be wondering, is this a function, is it not? Well, it definitely is a function because we used the notation f of x, and think about the vertical line test. When you run a vertical line across what appears to be where they two overlap, you will hit a closed circle on one segment, but then you will hit an open circle on the other. And since you're hitting an open circle, you're actually not touching a point on that piece. So this does indeed pass the vertical line test, and yes, this is a function. So please try example 3a and 3c on your own and have them ready to check for tomorrow. So that concludes video lecture number 10. As always, please take a moment to look back and write down at least one question you still have after watching the video lecture. Please have that ready to go tomorrow in class. Once again, thank you for watching, and good luck.